The next source of our additional abutment weight comes from the soil. Section B and the elevation views of the standard drawings help us understand this best, just like they did with the ramp walls. But unless you've been on site, this is a difficult concept to visualize. So unless otherwise specified, the ramp walls will go down to the depth to meet the bottom of the anchor. You can see this kind of highlighted here in green on the elevation view. But the fill will only begin around ground level or just below, depending how much you've needed to excavate to clear a path for your cables or to get to your foundation. So you can see the undisturbed soil in green here on the right, and you can see, the two dots I've drawn for the cables. So the ramp walls will meet the bottom of the anchor, but this fill, part of that fill might be left as undisturbed soil. Excavation is hard work, so we only dig up enough to give the cables an unrestricted path to the tower and walkway saddles. And this is a good point to note too, that if you need that extra sliding capacity for any reason in your design process, taking out that undisturbed soil and replacing it with fill is another way to add some extra capacity. And looking back at the elevation, we can see where I've noted that you will have to dig out a channel for the cables closer to the anchor, and I've highlighted in gold here what the actual fill behind the ramp walls, or rather, I should be saying between the ramp walls, is going to look like, the profile of that fill. And just to make sure we are all in agreement, the soil portion should be measured from the center of the cables to the top of the foundation. All right, from the center of the cables, right at this inflection point where it's not drawn super well, but where the gold and the green both turn all the way to the top of the foundation. To make and at this point, we can then calculate our three major quantities. Center of the cables. This is a better detail. I'd forgotten I'd written this out. Center of the cables here to the top of foundation. We'll not be counting that area below the ramp wall as soil because that's not going to be engaged with the entire abutment block, right? We just have this area below the cables from the center of the cables to the top of the foundation. And now we can calculate our total abutment fill area, our rock slurry abutment fill, which is the portion of the fill. If we're calling this all fill, a portion of the fill is going to be number 3, our undisturbed soil area, and a portion of the fill is going to be number 2, our rock slurry area. That's that portion of the abutment that we actually fill with rocks, fill with gravel, fill with varying sizes of rocks, and do lifts of a grout slurry mix to keep that all together. So the total fill area is going to be the combination of the slurry plus the soil. And also be careful during this stage. I wrote a note up here to make sure not to double count the back wall. I calculate the back wall separately as a weight, so I usually just go up to the edge of the back wall. And then you can measure the undisturbed soil, which is an easier measurement to make. And then just use the equation I've written out here to calculate the rock slurry fill to save some time in measuring AutoCAD areas. Or, as you're updating your design, this is one less area you have to take. But be careful when taking these values to only account for the soil that is on the same plane as the anchor to foundation line. This is what I was referring to and what I've written out in red. The reasoning for this is given in the following, which is really the reasoning why we include this undisturbed soil to begin with. So we can imagine this column of soil acting as a shear stud of sorts, sticking up from the ground and halting any movement of the anchor. And no part of the abutment is going to begin sliding until this soil starts moving. And part of this is what we've determined in the component analysis phase, when we're looking at individual components and their ability to connect to each other. Because of this all, we decide to add the weight of the soil to our entire block in sliding. However, to remain conservative about this assumption, we won't include the shear capacity of the soil in the passive pressure exercised by this soil plug. So you can imagine there's this soil shear stud, and not only is it just weight, but actually getting it to move, it's going to have some some sort of shear, you know, strength at that interface, and we're not going to include that because we don't want to be relying the entire bridge on the capacity at that interface, especially if for some reason there's a flooding event and it gets wet and then has no longer any shear capacity. So we'll ignore all of this, but we will use the soil weight. And then ultimately we can rewrite our P-ramp equation. You may remember from the basic course, the manual, or rather the binder. The P-ramp equation is the sum of the ramp walls, the slurry rock fill, and the soil weight. So this is going to be the entire weight of our ramp that we've discussed so far. Note that it doesn't include, this equation here doesn't include the ramp cap, which is something that you can either add into this equation or add separately. I like to add it separately, but now we've broken down our P-ramp into the ramp walls, which are our basic and our additional. We have the slurry and we have the soil.